Okay, now chapter 7, geometrical optics. Geometrical optics, first we have a 7.1, reflections at a spherical surface. So what does it mean by reflections? Reflections of light is defined as the returns of all or part of the beam when it encounters the boundary between two media. So the example given right here is the example for a plane surface, okay, but that is not our main focus in metrics. In metrics, our syllabus is going to focus more on the spherical surface. Okay, but before that, of course, you have to know what is the law of reflection. So the law of reflection is stated that incident ray, reflected ray, and normal line, they are all lie in the same plane. That is the first condition. And the second condition, when it comes to the law of reflections, you have to mention about the angle. So angle of incidence is equals to the angles of reflection. Okay, so the I and the R, they are equal. Why? Because now the light ray is moving in the same medium. Okay, so the angles will change if they change medium. It travels in a different medium. But right now, after it's being reflected, it's still moving in the same medium. So we will have the same angle. So that is the law of reflections. Okay, law of reflections. Two rays and the normal line, they are all lying on the same surface. And angles of incident and angle of reflections, they are equal. Okay, so that is the things that you have to know before we proceed to 7.1a. So this is just a quick recall, okay, the things that reminds you what does it mean by reflection. So now 7.1a, if you look at the learning outcome, the first thing that you need to know is that the radius of the curvature r is equal to the 2 times of the focal length. And then you have to know how to sketch ray diagram, which we have seen it yesterday. Okay, we have learned how to sketch ray diagram for mirror as well as the lenses yesterday. So spherical mirror is defined as a reflecting surface that is part of a sphere. So if you have a sphere, you take the inner surface, then that would be our concave mirror. Concave mirror is also known as converging mirror. Why? Because all light, they will focus at one point. Okay, all lights will focus at one point. And then when it comes to the second one, if you look at the second diagram, if you take the outer surface as the reflecting surface, then it is a convex mirror, which is a diverging mirror. Okay, all lights, they are going to spread out after they are being reflected. So there are 2 types of mirror, spherical mirror. It is a convex, which we say curving outwards, or concave curving inwards mirror. So we have 2 types of mirror. Okay, one is inside, inner surface, one is outer surface. And as you can see right here, how are they labeling the C? So when it comes to concave surface, C is in front of the surface. When it comes to convex mirror, then the C is behind the surface. Okay, it's behind the surface. So make sure you label it correctly. And then F is somewhere. Okay, it's a midpoint between your P, point P, and also the C. Okay, so next one, we're going to look at the terms in a spherical mirror. Okay, we have to know all these terms. We have to label it in our diagram. First thing, of course, you need the center of curvature. So the center of curvature is the center of sphere which curved mirror forms apart. And then radius of curvature, okay, radius is from point C until the point P, which is the pole, or we call it vertex. So it is the point at the center of the mirror. And then principal axis is the horizontal line, okay, horizontal line right here. This one, this whole line, we call it principal axis. And then paraxel rays, the rays that are near to or almost parallel to the principal axis. So curve AB is called the apertures of the mirror. So this curve, okay, this curve actually is just part of the mirror, okay? You're not taking the whole things. That's why in a sketching, remember the things that I told you yesterday, you use a straight line when it comes to sketching. So what is a focal point and focal length then? Focal point is just a point, okay, where all incident light, they converge after reflections of the mirror. So they are all going to focus at this point, okay? They are all going to pass us through this point. They converge at this point. So its focal point is a real because it's in front of the mirror. Whereas when it comes to a convex mirror, okay, it is the point where the rays seem to diverge from the F. Okay, they all spread out from this point, this F. And this F is located behind the mirror. And in this case, we call it virtual focal point. Okay, because it's inside, which you cannot see it. So a focal length is defined as the distance between the focal point and the pole or the vertex of the spherical mirror. So if it is in front of the mirror, if it is real, then we say it is positive value. When it comes to convex mirror, because it is virtual, therefore we use negative focal length. So remember the things that I told you yesterday. When you label the point, the focal point, you use capital letter F. When you label the length, the focal length, we use the small letter f. Small letter f represents length. Capital letter F represents the point. Okay, so converge means they are all gathering, they are all focusing at one point. Diverge means they are spreading out. So next one we have seen it yesterday. Okay, we have to learn what are the methods that can be used to sketch to indicate the positions of the object. So there are three principal rays that we can draw. The first one is parallel to the principal axis and then passes through F. Okay, passes through F. That is the ray 1. And then the second one passes through F and then reflected and parallel to the principal axis. Okay, so that is what I showed you yesterday. So the first one is we draw the line that is parallel to the principal axis first and then passes through F. The second one, you let it pass through F first and then you draw it parallel to the principal axis, a reverse process. And then the last one is just a passes through and then reflected back along the same path. Okay, passes through C and reflected back along the same path. So we have three different paths right here. So now let's look at one example as a recall process. So ray 1, it tells you, okay, ray 1, it tells you first, okay, the light ray is parallel to the principal axis. Okay, so parallel. Now, as you can see here, because the mirror given here is a curve, so what I'm doing right here, I draw a line, okay, a straight line, a dotted line behind the curved surface. And all light, they will be reflected along this vertical line. Remember, it's not being reflected by the curved surface. Why? Now, you have a mirror, okay? And then the light shines on this mirror, actually is a lot, okay? There are plenty of light shining on the same mirror. So what are we doing right here? We are just taking a very small part, a very tiny part of the mirror to sketch the ray diagram. And this tiny part, when we take it out, it seems like a straight line because we are just taking maybe just a 0.0 mm or 1 mm or something like that. A very, very, very small part of the mirror. That is the part that we use in our sketching. Okay, so now when it comes to this one, okay, so the first ray is parallel to the principal axis and then it's being reflected by this red color vertical line, dotted line. And then after it's being reflected, it will pass through F. Okay, it will pass through F. So this is our ray 1. Okay, ray 1. Ray number 2, okay, ray number 2 that we have right here. Okay, this diagram, we don't have ray 2. The next diagram, it is going to pass us through F. Through F, and then when it hits the vertical dotted line, then it's being reflected and goes back along, goes back parallel to the, being reflected back and travel parallel to the principal axis. Okay, so this one is an example of ray number 2. Okay, and then ray number 3, okay, ray number 3 is just a ray that is going to move forward and passes through C. And then when it hits the dotted line, it's being reflected along the same path. Okay, so going to and coming back along the same path. So we have 3 types of ray depending on the object. Where is our object? And we will have a different, we can choose a different type of the ray. Okay, and you just need 2 in order to identify the positions of image, like what I told you yesterday. So after you draw the diagram, then you state the image characteristic. Well, when it comes to image characteristic, we are going to follow the statement, the Burke's laws. Okay, where L stands for location, you describe where is your image, and then the orientation, whether the image is upright or inverted, and then the size, same size, magnify, which has become larger, or diminish, which has become smaller, and then the type of the image, real or virtual. So these 4 things you have to mention it in your image characteristic. Okay, so I will give you this handout later on, okay, with a complete ray diagram. So make sure you draw it in your books. Okay, you draw this 6 diagram in your books. So here they also give you the characteristic of the image. The things that you have to take note is when it comes to object at F. That is a special case. When the object is at F, image form at infinity. That is the only information that we have. We don't know whether it's real or virtual. We don't know whether it's upright or inverted. Okay, all we know is that image is at infinity. All right, so when it comes to an object at F, and the question asks you to state the characteristic, all you can state is that the image is at infinity. Okay, so ray diagram, we are done. Okay, we discussed it yesterday. So this one is for a convex mirror. So convex mirror, you have only one example. Okay, so all this image, all these positions, they are going to give you the same image. While your image L is behind the mirror. Okay, behind the mirror. And then O, it's upright. The size is always diminished. Okay, and then the type is always virtual, regardless of where is your object. But when it comes to concave mirror, okay, the positions of the object plays a very important role, because at a different position, you will have a different type of image, different form, different characteristic image. But when it comes to convex mirror, you have only one answer, and this is the only answer. This is the only diagram. All right. So this one, if you look at this ray, the ray is given right here. Okay, the ray used in this diagram is actually ray 1 and ray 3. Ray 1 means it's parallel to the principal axis, and when it hits the surface, the vertical line, it is being reflected. And the directions of this reflected ray is passes through F, the focal point. Okay, the focal point behind the mirror. So you extrapolate the line, and that would be the directions of the ray. Okay, the path of the ray. And then the second ray is the ray that is, okay, that is moving from the object and then passes through C. Okay, passes through C. So it is moving towards C and being reflected along the same path. So the crossing point behind the mirror, it gives you an image. Okay, where this image is the virtual image. Okay, virtual image, because it's formed behind mirror, and mirror is transparent by right. You cannot see it. In this case, we call it virtual. Okay, it's not formed in front. So we have a virtual image. Okay, virtual image right here, and then here we use ray 1 and ray 3. Okay, ray 1 and ray 3. We choose ray 1 and ray 3 in sketching. So the image, the characteristic is always the same. So remember, when it comes to this type of mirror, when you're going to sketch a virtual path, you use dotted line. Okay, so along the path along behind the mirror, you use dotted line. Okay, you use dotted line to indicate that now this is a virtual path. This is not a real path. Okay, so we are done with the mirror. Now let us proceed to the next one. Next one is the equations. Okay, we're done with the ray diagram. Now, when it comes to the equations, we have just one equations in a first subtopic, where 1 over F is equals to 1 over U plus 1 over V, which is equals to 2 over R. Okay, why 2 over R? Because we sub F equals to R over 2. Okay, R over 2. So that is how we obtain 1 over F equals to 2 over R. You just flip it over. So F is the focal length, U is the object distance, V is the image distance, R is the radius of the spherical surface, the distance of the between the pole and the center of curvature. Now, the important things when it comes to chapter 7 is that other than ray diagram, you have to be able to determine the sign convention. Okay, so the sign conventions that we have right here is for object distance, if you have a real object, or the object is always real, okay, it's always real in a mirror type question, then we use positive sign for U. Okay, so negative sign, we use it for virtual object distance. Okay, virtual object. And then when it comes to V, okay, when it comes to V, which is the image, if you have a real image, then image distance is positive. If you have a virtual image, then your image distance, you use negative sign. And then for F, okay, the focal length. So focal length is positive for concave mirror. It is negative for convex mirror. Now, what I want you guys to do, I want you guys to add in another physical quantity, which is m. The magnification, if you have positive magnification, then it means your object is upright, right? And then if you have a negative m, then it means your object is object is inverted. Your image is inverted. Okay, upright image, inverted image. Okay, upright image, inverted image. Depends on your m. And of course, okay, we also have another terms called h, the height. Height is positive if it is upright. Okay, if it is upright. So regardless of whether you're looking at the image height or object height, if it is a positive, if it is upright, then it's positive. Okay, and if it is inverted, then it is negative. Okay, I think you have it in the next table as well. Okay, but usually I like to put everything in one table. So here you have it. Okay, here you have it. So M is upright. Upright image, inverted image. Okay, upright image and inverted image. And then you have a H and H, HI and H note. HI represent image height. H note represent object height. Okay, so in your books, in your notes, they split into two, but usually I just put all them together. Okay, so if you want to keep it like a usual one, also can. Okay, now when it comes to M, magnification, linear magnification of a spherical mirror is defined as the ratio between image height and object height. And M is equals to, okay, because you're looking at the ratio, so it's HI over HO. Okay, and then it is equal to negative V over U. You must keep the negative. Okay, I know that if you are using your senior books, okay, the old revision books, they use modulus V over U. We no longer use that one. Okay, now we use equation M equals to negative V over U. Kita tak guna lagi equations yang ada modulus. Kalau kamu ambil buku senior Anda yang lama-lama punya, mereka pakai M equals to modulus V over U. Okay, tapi itu sekarang kita tak pakai sudah. Kita pakai yang ada negatif. So make sure if you are using your senior books, okay, you check whether there's a negative sign or not. Okay, if they are still using modulus, then means that is wrong. Okay, you need to change it into the one with negative V over U. So when it comes to a mirror type questions, usually we use real object. So if you have real object, then negative M is an inverted image, positive M is upright image. Okay, that's why in the table right here, okay, I asked you to add a image here. Positive M, upright image, negative M, inverted image. Now, other than upright and inverted, M can also give us a few other information, which is if the values of M, if equals to 1, then it means now the object and the image, they are same size. Okay, same size image and object. If your M is larger than 1, then it means your object magnified. Okay, magnified. If your M is smaller than 1, then it is diminished. Okay, it's diminished. So this one, you just look at the value without the sign convention. Okay, without the sign convention. Because the sign convention just tells you whether it is upright or inverted. But the value, the magnitude, it tells you whether they are same size, they're magnified or diminished. Okay, so for example, if you have a value M equals to negative 2, so this negative, now it tells you you have an inverted image. Okay, inverted image. And this value 2, it tells you now your image is magnified. Okay, you have a magnified image, means it's larger than the object. So the negative and the 2, you have to interpret them separately. Sign convention, it tells you upright or inverted. And then value, it tells you what happens to the image, whether it's the same size object, larger than object, or smaller than object. Okay, so I give you 1 minute to write it down. This is very important, all right? Because sometimes based on the calculation, questions will ask you to state the characteristic as well. Okay, so this is what you have to know, right? This is what you have to know. So again, if you have a positive sign, okay, if you have a positive sign, then it means you have a virtual image. Okay, if you have a positive M, then your image is virtual. If you have a negative M, then your image is real. Okay, you have a negative M, then your image is real. Real image. Okay, satu lagi yang kamu boleh sebut pasal M, if it is positive. Okay, if it is positive, then your your image is virtual. Okay, your image is virtual. If you have a negative m, then you have a real image. Provided if your object is real. Okay, the rules is that we have a real object right here. Okay, well we do. Okay, because in our syllabus we always use real object. Okay, we always real object. So if you have a real object, then that is what you can get from the values of m. Tengok, dari m sahaja kamu dah tahu semua karakteristik, even without looking at the diagram. Okay, without looking at the ray diagram. So okay, I give you well 1 or 2 minutes to write it down. Okay, then we will proceed. Okay, we'll proceed to the next one. So catat ya semua ini. Sebab dari M saja kamu sebenarnya boleh dapat semua karakteristik untuk kamu punya image. Okay, so next one. Okay, so we are done with a mirror. Okay, so basically that's all about mirror. You have to know how to sketch the ray diagram, and then you have to know what is a magnification. So next one, we're going to look at the refractions at a spherical surface. Now, before we look at the refraction at a spherical surface, we must first know what does it mean by refraction. So refraction is defined as a changing of directions of a light ray and its speed of propagation as it passes through from one medium into another type of medium. For example, if medium 1 is air, and then medium 2 is water. Okay, so if you look at your straw, okay, kalau kamu tengok straw yang kamu minum air, when you look at it from the side view, okay, you will see that it's like bent. The straw is like being bent. Why? That is because of the refractions of light. So the incident ray, okay, the incident ray, if it's traveled from medium 1 to medium 2, the angles will become different. Okay, either it's being reflected towards the normal line or away from the normal line. So when it comes to law of refraction, just now we have law of reflection. Now we have law of refractions. So when it comes to law of refraction, the first rule is that the incident ray, the refracted ray, and once again the normal line, they are all lying on the same plane. Okay, and then it obeys Snell's law. So reflect means you have to look at the angle, but when it comes to refractions, then we look at the Snell's law, where we know n1 sine I equals to n2 sine R. Okay, n2 sine R. So that is the Snell's law. Okay, you write it down. Okay, you record it in your books. Before we move to refractions at a spherical surface, okay, there are a few things that you need to know. Where I'm going to show you this one. Wait, yeah. This one. Okay, you have to know a few of the rules. What happens when it's traveling from denser to less than medium, from less dense to denser medium, and a special case. So if your N1 is less than N2, okay, if your N1 is less than N2, means that your medium 1 is less dense than medium 2. Okay, less than medium 2. So means that now, okay, if you look at the values of refractive index, it actually tells us which medium is denser. The one with a larger value is denser. Okay, for example, air and water has a higher refractive index because it's denser than the air. So now you have incident light ray traveling from less dense medium, and then now it moved towards a denser medium. Then what happened is that the light ray, it bends towards normal line. In this case, we have incident angle larger than refractive angle. Okay, refractive angle. If your medium 1 is denser than medium 2, means that now your N1 is larger than N2. What happened? Okay, so the incident light ray, when it's traveling from denser medium towards less than medium, the light ray, it bends away from the normal line, which in this case, now your incident ray angle is less than reflected ray angle. Okay, so that is the things that you need to know, because sometimes you might be asked to sketch the diagram. Okay, you might be asked to sketch the diagram. All right, then how about the special case? So there are a few special cases that you have to know. The first one is what happens if your light coming in at a 90-degree perpendicular to the surface. If it is perpendicular to the surface, then no refractions. Okay, it doesn't matter whether you're moving from denser medium to a less dense medium or from less dense medium to a denser medium. If it's entering the surface perpendicularly, then no refraction. And then another one is a critical angle. Okay, critical angle. So critical angle, if I'm not mistaken, is 42 degrees. Okay, so if your incident light ray is traveling at a critical angle, when it hits the surface, then the ray will be reflected and it's parallel to the surface. Okay, it's parallel to the surface. With a condition, the light ray must be coming from denser medium towards less than medium. If it is larger than critical angle, then total reflections occur. Okay, it will be reflected, not refract anymore, but reflect. Okay, internal reflections happen. So that is what happens right here. All right, these two are special case. Okay, these two are special case. The important thing is the first one. Okay, the first one. Why? Because next I'm going to show you how to sketch the diagram for a spherical surface. So this one is still a flat surface. How about spherical surface? So now let us go through the equation first. Okay, let us go through the equation first. So equations for a spherical refracting surface, we have an N1 over U plus N2 over V equals to N2 minus N1 over R. Okay, over R. And then the equations for a linear magnification is M equals to H image over H object, still the same, but for this one, for the V and U, it is N1 V over N2U, okay, N2U. But this is just an additional info. This is not in your syllabus, all right? So this one, you just have to take note, but you don't have to memorize it because it is not in your syllabus. In your syllabus, it's just this one, okay? So you have to know how to use this equation. Okay, now let's look at an example. How are we going to sketch the diagram and which part represent N1, which part represent N2? So you have a spherical surface. So this spherical surface, now we are going to take a spherical sphere as an example. Okay, if you take a spherical sphere as an example, so this is the center of curvature, and then this is the principal axis, okay, the horizontal line that passes through your center of curvature. So this is the center. Okay, so now my object is right here. For example, this is my object. So usually when it comes to this subtopic, we are going to take a point as an object. We are going to assume our object as a point object. Just like in our syllabus, okay? In reality, of course, your object comes with a size. But in our syllabus, what are we doing? We just assume it is a point object. So this point object, it means like in all direction. Okay, I'm just going to take one as an example. For example, this is the light ray. Okay, the light ray that I've chosen. So this is the incident light ray. Okay, your incident light ray. Now, how are we going to sketch the diagram then if you have a spherical surface? If you have a spherical surface, the things that you need is the normal line. Where is the normal line for a spherical surface? How are we going to know, okay, the spherical surface is pointing towards which direction? So remember, normal line is always perpendicular to the surface, okay? And when it comes to a circle, in order to obtain a line that is perpendicular to the surface at this point, then it means this point must be coming out from the center, must be parallel to the radius of the curvature. So this is the radius, okay, this is the radius, and it is always perpendicular to the surface. So meaning that if you extrapolate it, this is actually our normal line, okay, the radius at the same time, it is acting as our normal line because it is perpendicular to the surface at this point, okay, at this particular point. So now that I have the normal line, I have the incident light with an incident ray angle, the I. Okay, now next I'm going to determine where is my refracted ray. So let's see. Let's assume outside is air. Air, it comes with n equals to 1.0. This one, the glass sphere. Okay, this is glass. So glass, the n usually is 1.5. And then outside here again is air. Air again, I have n equals to 10. So now, if you look at my incident light ray, it's traveling from air towards glass, from less dense to a denser medium. It is from less dense to denser medium. Then what happened? Okay, what happened when it's traveling from less dense to denser medium? It will be refracted towards normal line. So you just draw a line, okay, where this R is less than I. Okay, R less than I in this case, because now you're traveling from less than towards a denser medium. Okay, less than towards a denser medium. What happens here is that if you look at this glass sphere, this light ray is being refracted twice. First time on this front surface. Okay, this is your first refracting surface. Okay, the first refracting surface. This one we call first refracting surface. After it is being refracted by the first surface, the light keeps traveling and now it comes to the second surface. Okay, the surface at the back. And this is what we call second refracting surface. So light is actually being refracted twice as it passes through a transparent medium. Okay, a transparent glass sphere. In our syllabus, we look at glass sphere. So as it passes through this glass sphere, it is being refracted twice. Then what happens in the second surface? So in this second surface, again, we need the normal line. Okay, we need a normal line. So this is my normal line. Okay, so this is my incident light ray. Okay, now this ray is acting as my incident light ray. As it's approaching this point, okay, as it passes through this point, now it's traveling from a denser medium towards a less dense medium. Okay, a denser medium towards a less dense medium means that when it's being refracted, it's going to move away from the normal line. So in this case, your R is larger than I because it's traveling from glass to air. Okay, so now it's away from the normal line. So that is what happened actually when your light ray passes through a glass sphere. Okay, when your light ray passes through a glass sphere. So that is the diagram. Now, of course, the ray diagram, I'm not sure whether you will be asked to sketch the ray diagram or not, but you have to know there are two refracting surface, and where is N1, where is N2. For first refracting surface and second refracting surface, they have different N. When it comes to first refracting surface, okay, you have to know where is the incident light ray. We always take O as our directions of incident light ray. Okay, we're going to look at O. We're going to take O as the front part. So when it comes to the first surface, okay, when it comes to the first refracting surface, in front of this surface, we call it N1. Behind it, we call it N2. When it comes to second refracting surface, the glass is no longer N2, but now it is acting as N1. Okay, it is acting as N1, and then behind it is acting as N2. So that is the values that we're going to use in our equation. Okay, that is the values that we're going to use in our equation. N1, N2 for the first surface, the one in the green color, and N1, N2 in the purple color for the second surface. So when it comes to calculations, quite often you have to calculate the same thing twice because your light is being reflected twice. Don't worry, we will do an example after this. So you will have a better idea on what does it mean by it's being reflected twice. What does it mean by we have to do the calculation twice? Okay, one for the front surface, another one for the second surface. And one more thing, okay, now since you have two different surfaces, we also need to know whether the R that we're going to use is positive or negative. Now let us go back to this table. So the sign conventions when it comes to this equation, okay, U and V is still the same. U, if you have real object, then you use positive, virtual object, you use negative. When it comes to V, real image, positive, virtual image, negative. But now this one, V is real, is virtual if it is in front of the surface. Okay, you have a real image if it is behind. Why? Because now you have a transparent surface. By right, by common sense, the light should pass through it. And the image, by common sense, should be formed behind the transparent surface. So if it is formed in front of the refracting surface, then you have a virtual image. Okay, then you have a virtual image. Now, the important things in this one, okay, in this table is that how to determine the sign convention for R. Okay, how to determine the sign convention for R. What does it mean by convex surface? What does it mean by concave surface? Okay, what does it mean by convex surface? And what does it mean by concave surface? So convex surface, okay, convex surface means that now you have a surface. This is your incident light ray. Wait, let me choose a color. So this is your incident light ray. Okay, this is your incident light ray. If you have a curve that is curved towards the light ray, then this one, we call it convex surface. Okay, this one is convex surface. When it comes to convex surface, we substitute R as positive R. Meaning that if you look at the diagram just now, the green color surface is the convex surface. The first refracting surface is the convex surface, and you have positive R right here. What does it mean by concave surface? So again, you still have an incident light coming from the left-hand side, but now the curve is away from the light. Okay, you curve away from the light. Just now it's towards the light, now it's opposite to the light. So in this case, we call this concave surface. Okay, concave surface. And in this case, you have negative R. Meaning that let us go back to the original diagram, to the diagram that I sketched just now. The purple color surface is a negative R surface. Okay, it's negative R. Why? Because my object is located on the left-hand side here. So my incident light ray, regardless of which surface that you're looking at, it's always coming from the left-hand side. Okay, we take the directions of incident light ray from the left-hand side. So first surface, convex surface, second surface, concave surface. So you have different R, different sign conventions for both surface, and then different N1 and N2 for both surface. That is the things that you have to know when it comes to calculation. All right, so this is the new things to you. I will give you some time to write it down, okay? So the diagram that I draw here is not in your lecture notes. So I hope you can draw it, okay? I hope you can draw it in your books. So I will give you 5 minutes to complete the diagram here. Okay, kamu guna sedikit masa untuk lukis diagram di sebelah kiri ini, di dalam buku Anda. Okay, di dalam buku Anda. So perhaps you can use different color for different surface so that you can see what is going on. Okay, what is going on. So I've showed you how to draw the ray diagram for a spherical surface for a glass sphere, and then I've showed you how to determine N1, N2, and how to determine the sign convention for R. Okay, how to determine the sign convention for R. So now I give you 5 minutes to draw the diagram in your books. Okay, sendiri lukis diagram ini dalam buku Anda. Okay, so well, before we proceed to the next part, there's one thing that I forgot to mention just now. Now, the radius of curvature, the r, other than for convex surface and concave surface, we have another possibility where it is a flat surface. Flat surface. If you have a flat surface, then what is the value for r? R is equals to infinity. Okay, r is equals to infinity, meaning that you cannot do the calculation. All right, so that can happen, okay, especially in the following subtopic where we have a plano convex lens and the plano concave lens. Okay, so when r, okay, when it comes to the flat surface, then we assume the radius is equal to infinity. Okay, the radius is equal to infinity. If you have a flat surface, For example, like the plano-convex and plano-concave right here. Okay, so the last subtopic in chapter 7 is thin lenses. Thin lenses is defined as a transparent material with two spherical refracting surface whose thickness is thin compared to the radius of curvature of the two refracting surface. Okay, so basically you combine the two surfaces together. So if you have a two convex surface, then you call it biconvex lens. Okay, biconvex lens. When you have a plano-convex, one flat surface and one convex surface, then we call it plano-convex. You have a two convex like this one, we call it convex meniscus. Okay, the second one, you have biconcave, plano-concave, and concave meniscus. Now you have to know the name and the shape. Okay, you have to know the name and the shape. Why? Because sometimes questions will just mention the name without telling you, without giving you the diagram. So for example, it tells you now you have a plano-convex lens, and then it asks you to calculate the focal length, for example. Then you yourself have to know the shape in order to determine the sign convention for each of the shape, okay, each of the lens, each surface. So now let's see, how are we going to determine the R, okay, how are we going to determine the R for the convex, plano-convex, convex meniscus, concave, biconcave, plano-concave, concave meniscus. So for example, now you have two types of lens. Okay, so when it comes to R, how are we going to determine the sign conventions? Okay, you look at the directions of the light ray. Okay, now I'm going to skip it first. Okay, I'm going to skip it first. Let us go through the ray diagram first, and then after we proceed to the equations, I will come back to determining the sign convention. Okay, I think that will be better, because right now, if I explain the R to you, I think you still cannot imagine what is going on. Okay, so I'm going to skip for now first. So now let's look at the terms in thin lenses. In a thin lenses, okay, we sketch it. Okay, the center of curvature. So usually we use 2F, okay, rather than C. 2F1, 2F1, F1, and then F2 and 2F2. Okay, we seldom use C in our diagram. So center of curvature is the center of a sphere for the of which the surface of the lens is part. So this C, okay, this 2F1 is for this surface. Okay, it is for this surface. And then 2F2 is for this surface. Okay, it's for this surface. So that is your F. Okay, that is your F. The first one is for the green color one, and then the F2 is for the blue color one. And then you have the radius of curvature. Well, we're going to use it in our calculations. And then the principal axis, as usual, is the horizontal line. And then optical center. Okay, we have a center right here, which we call it optical center. So optical center is very important because one of the path of the ray, okay, is going to travel through this optical center. So again, we have the focal point and the focal length. Okay, focal point, again, is the part that you have all light that is converged and also the diverge. So for concave lenses, okay, for concave lenses, the focal point, okay, the focal point is the point where all this line, it seems to be diverged from, okay, diverged from F1. If you're convex, then they're going to converge through the F after passing through the lenses. So when it comes to concave lens, it is virtual. Convex lens, it is real. Okay, that's terbalik to the mirror. Mirror, concave, you have a virtual focal point, and then convex, you have concave, you have a real focal point. Convex, you have a virtual focal point. That is for mirror. Okay, so F is terbalik for mirror and the lens. And then the sign convention, when it comes to concave mirror, you have a negative F. And then, so when it comes to convex lenses, you have a positive focal length. Okay, all this, you can just memorize it. Then the ray diagram. So once again, we have three types of a ray. Okay, ray 1 is parallel and then passes through the axis. Okay, a parallel and then passes through F2. And then ray 2, okay, through center of the lens and then coming back along the same path. Okay, and then ray 3 through F1 and then emerge parallel to the axis. So how? Okay, I'm going to explain it quickly again. So first one, okay, your ray one, it starts from parallel to the principal axis, and then when it touch the optical line, okay, it will all converge and passes through F2 behind the lens after it emerged from the lens. So this is your ray one. Okay, ray one, parallel first, and then through F. Okay, through F. And then ray number two is the ray that passes through optical center. Okay, so it passes through the optical center, and then heading back towards along the same path. Okay, go and back along the same path. So the crossing point, okay, the crossing point may be somewhere here. That is your image. So don't worry, I will give you the complete answer later on. Okay, I'll give you a complete answer as well. So this is the diagram. All right, you have the ray one and then ray two. And then how about ray number three? Okay, ray number three, we use it when, okay, we use it when we have, we use it when, okay, no, we don't use ray number three right here, okay, we seldom use ray number three right here. But of course, if you want to use it, also can, okay, also can. So when it comes to ray number three, you just let it pass through the F, and then when it hits the vertical line, okay, it emerges parallel. So that is your ray number three. Okay, ray number three. So F and then parallel. Right? So ray one is parallel and then through F. But the F is behind. This is your ray one. Okay, parallel and then through F. And then the second ray is through the optical center. Okay, through the optical center and then heading back along the same path. This is your ray number two. Okay, ray number two, center to center. Ray number three, F to parallel. So I'll give you this handout after class. Okay, so you don't have to write it down right now. Just focus on what is going on. Okay, and once again, when it comes to a object at focal point, okay, when it comes to object at focal point, or you can say its image is at infinity. And in this case, when it comes to lens, the additional info that you know is that it is inverted. Okay, it is inverted. That's it. All right. Okay. So now let us go to the equations. So this lens formula, okay, we have two formula. The first one is 1 over F equals to 1 over U plus 1 over V. Okay, so this one is just for you to calculate the object distance and the image distance. What we are going to focus on is the lens maker equation, a new equations to you, which is 1 over F equals to N2. Okay, N2 is the mediums of the materials, and then over N1, the refractive index of the material over the refractive index of the medium, minus 1 bracket 1 over R1 minus 1 over R2. Okay, minus 1 over R2. This is the lens maker equations, and usually we use these equations to determine the focal length. Okay, so N1 is the refractive index of the medium, N2 is the refractive index of the lens material. So this one is our lens. This is the lens. Okay, so this one is your N2. Okay, this one is your N2. Refractive index of the lens material. Okay, refractive index of the lens material. And then the surrounding, okay, the surrounding is N1, okay, which is the medium. Where did you put these lenses? Can you can put it in an oil, in a water, in any other medium, depending on the questions. So this is the refractive index of the medium, okay, of the medium that surround your lens. So if you put it in the water, then your N1 is the N for water. If you put it in the oil, then the N1 is the N for the oil. Okay, so linear magnification is same as a mirror. M is equals to Hi over H naught, which is equals to negative V over U. Okay, negative V over U. And once again, the information that you can get from this equation is same as the mirror. Okay, especially when it comes to the positive and negative sign convention. If you have a positive sign convention, then you have upright image. Negative sign means the inverted image. Okay, and then M, once again, you have M equals to 1 means same size. M larger than 1 is a magnify. And then M less than 1 is diminish. Okay, idea is the same. Okay, the way you apply this equation is exactly the same as the mirror. The only new things, the only difference between mirror and the lens is in these equations. Okay, in the lens maker equations. So the way to determine the sign convention, more or less, they are the same. So you have a U for real object, positive, virtual object, negative. V, real object, real image, positive, virtual image, negative. F, converging lens, positive, diverging lens, negative. Now, R, same as the spherical surface just now, convex surface, positive, concave surface, negative. H1, image height, positive is upright, negative is inverted. Object height, upright, positive, negative, inverted. Okay, negative, inverted. Now, let us go back to the diagram just now. Okay, that will be the last part of this section, this chapter. Yeah. Okay, this 6 type of a lens. Okay, now we're going to learn how to identify the R. Okay, whether it's positive or negative, and whether it is R1 or R2. So we have equations 1 over F equal to N2 over N1 minus 1, and then bracket 1 over R1 minus 1 over R2. So what are we going to do right here? Okay, first of all, we need to identify where is our incident light. Our incident light is coming from the left-hand side or the right-hand side. So let's assume, okay, let's assume my incident light, they are all coming from the left-hand side. Okay, my incident light, they are all coming from the left-hand side. So this is incident light ray. Okay, incident light ray means that that is a place where you place the object. Okay, this is your object. So object, it has a light coming out from the object. The light is now traveling towards my biconvex lens. So the first surface that is facing the object, that would be my R1. Okay, this one is R1. This surface is R1. So this R1 is positive or negative. Now you look at this surface and look at the light. This surface is now convex towards the incident light. So if it's convex towards the incident light, means that now this is a positive R1. Okay, this is a positive R1. So after the light ray passes through the first surface, it will keep traveling towards the second surface. When it hits the second surface, okay, when it hits the second surface, now this surface, it will give us R2. This surface, it will give us R2. But because now it is concave towards the incident light ray, so this R2 is a negative value. So now even though you have both biconvex, okay, we say two convex surface, by right it should be two convex surface, but when it comes to facing towards the incident light, one is convex towards the light, one is concave towards the light. So two of them, they have opposite sign, one positive and one negative. Okay, one positive and one negative. Now, can I have a case when I have a convex, biconvex, but now I assume my light is coming from the right-hand side? Can or cannot? Yes, you can. It is up to you to choose. Where is your incident light? Okay, if the questions didn't give you a diagram, the questions doesn't tell you whether the light is coming from the left-hand side or the right-hand side, then it is totally up to you to assume the incident light ray is coming from the left-hand side or coming from the right-hand side. It won't affect the final answer. It won't affect anything. Okay, the only difference is that now your R1 and R2 will change position. If your incident light ray is coming from the right-hand side, then this one would be R1. Okay, this one will be R1. And because it is convex towards the incident light ray, this one is now a positive R1. Okay, whereas the other surface is now acting as a concave towards the incident light ray. So it's a negative R2. Okay, it's negative R2. Now let us look at plano-convex. Plano-convex, the first surface is convex towards the incident light ray. So this one is positive R1. But if you look at the second surface, now this second surface is a flat surface. Okay, it's a flat surface. When it comes to a flat surface, then it means your R2 is actually equals to an infinity. Okay, infinity. So when it comes to calculation, okay, 1 over R2 is 1 over infinity, which is equals to 0. Okay, if you have an infinity radius, then 1 divided by infinity, it is equal to 0. So now let's look at a convex meniscus. Convex meniscus, this is the first surface. Okay, this is the first surface. So this is R1 and it is convex towards the incident light ray. So positive R1. And then the second surface, again, if your light, after your light passes through R1 and it keeps traveling. So the second surface is also convex towards the incident light ray. So in this case, my R2 is also a positive value. Okay, so convex meniscus, you have positive R1, positive R2. If your light ray is coming from the right-hand side, then it means you have two negative values, negative R1, negative R2. Okay, so for example, if this is your convex meniscus, okay, and then your incident light ray is coming from right-hand side, then the first surface is concave towards the incident light ray. Okay, concave towards the incident light ray, negative R1. Then the second surface is also concave towards the incident light ray, so you have negative R2. Okay, but it won't affect your final F. Okay, the values of a focal length is still going to be the same. Okay, it won't change anything to the F, to the focal length. Then the second one, converging lens. So once again, I'm going to assume the light ray is coming from the left-hand side. Okay, and my object is on the left-hand side. So this is the incident line. So when this light ray hits the first surface, this surface is concave towards the incident light ray. Okay, concave towards the incident light ray. So negative R1. Whereas the second surface is convex towards the incident light ray. So positive R2. This one, concave towards incident light ray, negative R1. But now the second surface is a flat surface. So once again, R2 is equal to infinity. When it comes to concave meniscus, the first surface is convex towards the incident light ray, so positive R1. The second surface, once again, is convex towards the incident light ray, so positive R2. Now, what is the difference between convex meniscus and the concave meniscus? How do I tell whether it's convex or concave? You look at the edge. Okay, kamu tengok hujung dia. So for a convex, okay, these two ends is smaller, is thinner than the center. Okay, it's thinner than the center. When it comes to concave meniscus, these two ends is thicker. Okay, it's larger than the center. Dia punya size di hujung lagi besar daripada tengah-tengah, itu kita kata concave meniscus. Kalau hujung dia lagi nipis daripada tengah-tengah, then we call it convex meniscus. That is the main difference between convex and concave. Okay, convex gemuk di tengah, concave gemuk di hujung. Okay, gemuk di hujung. So I give you 5 minutes to write it down, to record it. Okay, to record these things because it's very, very important. Students always got it wrong because you got the wrong sign convention. Okay, you got the wrong sign convention. So I give you a few minutes to write it down before we proceed to example 1.